20 years of experience in Singapore and Southeast Asia. So without further ado, may I hand over to Ms. Mario to start the presentation. Thank you.
Good evening, Leslie. Thank you for the introduction. And thank you everyone for joining. There are so many participants today, so we are really happy that you're interested in grouting. Today I will share the presentation with Tristan, which is our senior operation manager. I am the design manager for Keller Singapore. Today I will give you first a brief introduction of Keller to just explain who we are and where we work. Then I will take you through the first part about rock-fisher grouting. I will then hand over the presentation to Tristan, which will talk about cavity grouting, compaction grouting. And then he will conclude with 2 case studies. And at the end we will have some Q&A session. Keller is an international company. So we have around 10,000 employees all around the world. And we mostly operate in 3 geographical areas: in North America, in Europe, and what we call EMEA, so Asia Pacific, Middle East, and Africa. Singapore is the main office for the Asian business unit. So from Singapore, actually, we deal with projects all over Asia Pacific. We work in Malaysia, Philippines, Vietnam, and Indonesia. The ground improvement techniques we offer in Singapore, they go from vibro techniques, so vibro compaction, stone columns, gravity stone columns, to soil mixing, both deep mixing and shallow deep mixing. And then we have micropiles, ground anchor, and a wide range of grouting products. Today we are going to focus on rock-fisher grouting and compaction grouting. In terms of how we categorize ground improvement, we generally refer to the effect of the ground improvement into the soil. In this case, for the rock-fisher grouting, we talk about injection grouting, so we are under the chemical modification of the soil. And for the compaction grouting, actually the compaction grouting has 2 effects. The first one is the densification of the soil, and the second one can be used also as reinforcement. Today we will mostly refer to the effect of the densification. So starting with the rock-fisher grouting. The methodology, I am pretty sure everyone is familiar with. So there is a borehole that is penetrated into the ground through a rotary head. What I really want to highlight here, all our equipment is set with real-time monitoring. So you can see here there is a screen that in real time will monitor the execution. And this is also connected to a cloud. So we're really proud of our system, and we will show you a bit later how it looks like. In terms of grouting strategy, this slide, there is a lot of information. I just quickly take you through, and then we will break down slide by in each slide one item. Generally, the grouting strategy depends on the rock condition, and we need to tailor to the rock condition everything. So the drilling methodology, the sequence, and this also implies to select the right ports and systems, the ground mix, of course, and all the operational parameters. Today I'm going to focus on a single phase grouting. I will show in the next slide how we pick between bottom up and top down. And then I will elaborate a bit more on what ports and systems are needed for each sequence. Then I will give you some insight on how we select the ground mix, what are the most important parameters and why. And we will skip the part about the grading parameters because we have so much information we couldn't fit everything in this time. So starting with the sequence. When we have a stable rock, it's possible to use an ascending stage method. This means we will drill the hole to the bottom, so to the bottom level where we have to start our grouting work. In this case, with stable rock, we don't need to use casing. So what we do is we will start to inflate back stage we want to grout. Generally, these stages are around 5 meters. So when we inflate the packer will react against the stable rock itself, and then we will grout below. And each time then we will lift the packer and go progressively grouting upwards. This method is of course the fastest because we are just drilling one go and we don't have to wait any time to different stages. However, the limitation is this is only applicable for stable rock. When we have unstable rock, we need to move to different methodology, and I will present three types of possible approaches. The first one is called descending stages method. So in this case, we will start oppositely to the other one from the top of the rock. So we will insert the packer wherever inside in the top of the rock. Then we will grout, and then we need to wait until this grout is set and stabilize the ball. So then we can proceed with the drilling, and we will inflate the packer now against the rock that was stabilized in the previous stage. So this method is very effective, but the limitation is quite slow because every time you need to wait 2 to 3 hours minimum to wait for the rock mass to be stabilized because you can advance with the borrows. So to overcome this challenge, then there are other methodologies that can be applied in unstable rock. The first one is the end of casing method. So in this case, the borehole is advancing to the rock with casing to the bottom, and the packer will be inflated inside the borehole, and it will push through the casing. Then we will start to grout from the bottom, and then slowly lifting up the casing, and lift the casing only above the previous grouted stage, so then we can inflate the packer inside. However, there is a limitation here, because when we install the casing, there will be disturbed zone between the casing and the external rock. So this will become a preferential flow path. So when the grout is injected to very high pressure, the grout will tend, here you can imagine the rock is unstable, so probably it's very permeable. So when you go to inject here in high pressure, you might have some grout that start to find this path and then goes up. And actually we have observed, like there are different case studies where there were unusual readings, and this because the grout was actually not going here where we need it, but it was blowing up. So for this reason, this methodology is mostly used with the lower injection pressures. Mostly we can adopt it as a pre-consolidation. So when we just need to do a grouting very light, not really to achieve like a low permeability, just to prepare either for a second round of injection or for different jobs that don't require a very low permeability, this can be used. Otherwise, we need to move to the third methodology. This one is called MPSP, which stands for multi-port sleeve pipe method. So in this case, we will drill a borehole with the casing, and then we will insert a rubber sleeve with inside a tube with pipes hole. And then once we have inserted this, the casing can be removed. In this case, what we do is we will have single-use inflatable bags outside the pipes. So these bags can be inflated through the rock, and this one will prevent basically the flow to go up. It will prevent what happened in this case. So this method is much more effective compared to this one because we are actually sealing the outside of the tube to the soil, to the rock. Then once we have sealed, then we can insert inside the injection system with the packers, and then isolate with the packers the area that we want to grout, and progressively start to grout from bottom up. So this system is actually the best compromise, the best performance, but still not compromising too much on the timing. Something also I want to highlight is this methodology really requires an experienced contractor to do it, because the inflated bags are mostly effective when they are inflated against a stable ground or stable rock. This because if the rock around is stable, it means it's less permeable, so this seal will be much better, it will work much better. So we will not have a constant length stages. In this case, every stage might have a different length, because the operator will decide to inflate the bags at the level where we have encountered the most stable rock, so the performance will be better. Now we move to discuss the selection of the grout material. It's important for grouting to have a balanced, stable grout. What does it mean? So balance means the grout has to be homogeneous, and it has to have the right property, especially in terms of penetrability, to achieve a combination of the grout. Stable means yes, stable in terms of resistance to pressure filtration and bleeding. The resistance to pressure filtration is important because generally rock friction grouting will inject a very high pressure. So we need to prevent then the cement and the water are segregating. This is very important, otherwise the bleeding, even if we have pressure in the first place, it might change later during the grouting work. Plus, if there is a segregation, we might have like a tape around the injection system, and this would prevent the further grouting to penetrate. So we will read a bit out of pressure when actually we haven't really filled the rock around, or we just have a kick because our initial ground is segregated. So this is very important for the stability of the ground. For the penetrability, of course, I think we are all familiar with the importance of the grain size. Generally, the largest particle that are in our ground mix has to be no larger than 1/3 of the opening of the fissures. This is because we need, of course, the particle to move inside the fissures. And for this reason, of course, when we have like smaller and smaller fissures, we can go from OPC to microfine cement, in some cases ultrafine cement, despite this is not very used in Singapore. For the rheological properties, I also summarize here all the testing we can do. It's very important to check the cohesion. The cohesion determines how far the grout can travel from the grouting point. And the viscosity mostly influences the flow rate, so the speed at which the grout will flow. These two parameters are quite important in the selection of the grout mix. There are different methodologies. The pan viscometer, we will measure both of them separately, the cohesion and the viscosity. However, this test is very slow. We never use it in the actual practice. In practice, we use the Marsh cone, which will give us an apparent cohesion, which is then the combination of the cohesion and the plastic viscosity together. Typical values for the Marsh cone should be less than 45 seconds as an indication. Then bleeding is important because once the grout is set, we don't want the grout to lose volume, to lose water, because otherwise we go in the first round, we will close all the fissures, but then once the grout is closing, then smaller fissure will be open. So our work will be compromised in some way. So for this reason, we have to carry out the implementation test to make sure also the grout is stable in this regard. And the pressure filtration coefficient, as you see machine here, is what we have discussed before. So the resistance to pressure filtration. So you see here in the image, this is a kit where we have the instrumentation for the density. This is the Marsh cone, and then these are the other two tests. For bleeding, usually in Singapore, we tend to achieve less than 5%, and the pressure filtration coefficient usually has to be less than 0.05. I want to spend a bit more time now talking about the viscosity, because this is not really a value like before I told you, usually we can go with something less than 45-second marsh cone. But actually the viscosity, the apparent viscosity is very important because it's related to the amenability of the ground. The amenability is the ability of the ground to penetrate into the rock mass. So this one will determine really the amenability, how well the grout will flow, how far it will flow, and basically the success of the grouting process. It all depends in really getting these parameters right. So in the next slide, I'm gonna elaborate a bit more on the amenability. But before, I need to introduce our actually recall, because I'm pretty sure you are all familiar with the Lugion test. So Lugion test is a test that measures the water intake inside a borehole under a constant pressure or variable pressure. So generally, the Lugion can be conducted in a single stage where the pressure is maintained constant during the test, or in 5 stages where the pressure is first increased to the reference pressure and then reduced. This will give us an idea of the permeability of the rock mass, and is way more suitable, I would say, for the rock fissure grounding and generally dealing with fractured rock, because permeability is more referring to an homogeneous material, at least in one direction of definition, while in rock engineering we refer to a rock with a variable fissure, variable qualities. So actually really having a measure of water loss into a borehole is much more representative compared to just a permeability value. So remember what is the Lugion. Now we go back to talk about amenability. So amenability, as I mentioned before, describe how well the ground and how far the ground can penetrate into a rock mass. And this concept was introduced in 1995 by Nauzi. It's a function, of course, of the type of rock, the fissure, and the amenability depends on the rock itself and, of course, on the properties of the ground. The formula is very simple. So the amenability coefficient is the Lugion of the ground. This one we call apparent Lugion because it's actually done in a different way, and the Lugion of the water. The way we use this formula, usually what we do is we assume that the apparent Lugion can be calculated as the Lugion of the water times the ratio between the viscosity of the ground over the viscosity of the water. This is usually 26, 28, depending on the water we are working in. So, assuming this formula, we can set a value that we want for the amenability coefficient. Based on our experience, usually we aim for a 75% because we want the ground not to flow as well as water, otherwise if we lose it too much, there will be so much wastage and it would be difficult to control. But we also don't want a very low value because otherwise it would be very difficult to make the ground really penetrate sufficiently into the rock mass. So 75% usually is a good value. So based on this value, we want to back calculate the viscosity that we need for our grout mix. And this is how we pre-design the grout mix. Then during the operation, we start with the initial design of the grout mix, and then with the real-time monitoring, we can adjust it during the operation. So in terms of monitoring, then I will show you what we need to actually do all this adjustment during the operation. We have a pressure gauge transducer, flow meter, and then all this data, they are electronically recorded into our system, and real time they are shown in this screen that you see here, and then this is how it looks like. And also in real time, the system can produce this type of graphs. I hope you can all read that. This one is time, And then here you can read the concrete pressure, and here you can read the flow. So this, for example, is a typical example when you see slightly during time, so starting from zero, the pressure will build up and the flow will reduce until the flow suddenly drops, and then the pressure is maintained for 5 minutes. So this example I've shown you is a typical example of a pressure cutoff. And Tristan, in the case studies, will show you how this monitoring are studied, all the process engineering we usually do during our project. And I will now pass the presentation to Tristan, which will continue with the gravity grouting and the case studies.
Hi Tristan, you need to unmute. Tristan, you need to unmute. You know how to unmute?
Oh yeah, yes.
Now we can hear you. Okay.
Okay. Thanks, Ellie. So next I will bring you all through a method that we introduced to treat cavity in Singapore, and it is called a compaction grouting technique. So compaction grouting itself is a technique that can be used to treat cavity. Cavity is a feature that exists in karstic limestone profile. So when we mention about cavity, it's really just one type of the feature that we can find in limestone, and limestone is famous for the variability. So within the limestone formations, there are different type of geological features such as the fissure, the pinnacle. Sometimes we encounter solution channel that connects far away. The other two that are more commonly presented challenge in Singapore is a slump zone, which is a zone that actually was throughout a period of time, certain volume of the soil has been lost. 20-30% of the soil has already been lost through the connected cavity channel, resulted in a layer of very, very soft soil at a very deep depth. And of course, the most common feature that we all know are cavity. And inside cavity, there's two different types, whether it is infill or whether it is empty. So if it is infill cavity, certain material has already went in and filled it up. So there are different methods that we have to tackle it. And if it is an empty cavity, then it is another different challenge. So the challenge, of course, to the underground construction is, imagine if we need to sink in a shaft here for TBM, or if the TBM were to actually go through this formation, which is highly variable. So in the case of traditional foundations, all the limestone will also create different challenges for either the board pile or the driven piles. So these are all the challenges that come with limestone formation. Singapore is having some limestone formation, but not as bad as Malaysia. Well, we did quite a lot of limestone grouting in Malaysia. Nonetheless, I think throughout the years, we have seen more and more projects that are facing difficulty and challenges from limestone formations. So thus, a few years ago, we started bringing techniques of what we call compaction or groutings. So this is a method where, similarly to the rock fissure grouting, we drill in with or without casing into the desired treatment zone, and instead of pumping cement grout, we actually pump in a stiff cement mortar. And this material is what we call a low mobility grout. So the difference between this and fissure grouting is really because the fissure is very small, so we want to use a more flowable material to seal up the fissure. But when it comes to cavity and slump zone formation, because it's so flowable, we need a material that we can inject in a controlled manner, and something that is too flowable will be too difficult to control. So this is a concept behind low mobility grout. The applicable soil is all wide range. In the in the case of gravel or compactable sand, compaction grouting works by compacting the sand surrounding it, so it displays the soil away and densifies the soil surrounding it, the sand surrounding it. But if we come to a silty sand, it may be densifiable, but the pumping rate becomes very important. We must allow sufficient time for the pore water pressure to dissipate. So when it comes to silt and clay, compaction grouting mainly works on a reinforcement basis. So this ACOR earlier what Ellie shows in the table, whereby compaction grouting can actually work in both purpose. One is on reinforcement, another one is on the densification application. When we decide a grouting strategy for compaction grouting, the main criteria, of course, similar to rock fissure grouting, is what kind of volumes that we need to pump in, what kind of pressure that we need to pump in, and it's a function of the soil, and for the pressure, it's also a function for the depth of the treatment zone. Then, based on this, we will have to fine-tune the low mobility grout heights. Mainly we control by adjusting the slump of the material that we pump in for different type of the cavities feature. The layout and spacing will also form an important part. I will show you all later on this. After we decide this, then the next thing is actually the injection sequence, internal horizontal injection sequence. Meaning, do we do by a closure method, or we do by a from inside out, or do we actually do a split spacing method? So we start with further big spacing, and then we come in between and come in between. Vertically, the sequencing is impacted by what Ellie had explained about whether the rock is stabilized or not stabilized. In different kind of rock situation, the grouting sequence, vertical sequence will have to be adjusted. The injection rate is a function, of course, what kind of cavity and what are the infill material that we are facing. For certain compaction grouting whereby it is being carried out at a very shallow depth, often less than 5 meter or 5 meter depth, heaving may be the issue. So sometimes, even though we would like to achieve certain kind of displacement, but we will be limited by the heaving on site. When this kind of sieve material is injected using a control grouting, stage by stage, typically in Singapore, we are using every half a meter, 1 injections. So we allow the stiff material to form a spherical shapes. In the idealized situation, it forms a spherical shapes, and by pulling this up at every 500 mm, we form a sequence of this idealized sphere that will form the whole column inside the soil that we want to reinforce. However, this is also a function of what kind of soil are we dealing with. So even with the same type of pressure, at a stiffer layer, the intake will be smaller and resulting in a smaller idealized diameter. And at the softer layer, we will often see that a bigger intakes. In the case of empty cavity, we are not able to actually control the shape of the grout. Basically, the grout will just flow and fill out the empty cavity. So you will take whatever shapes the empty cavity is, and in terms of the slump zone, or where the cavity is already infilled with material, this is where we are able to form a grout column, a mortar column that can reinforce the soil. Depending on the infill condition, so as we are proceeding with the grouting, we will have to detect the infill condition of the cavity. Then actually the mix design ideally should be adjusted based on it. So in the scenario 1, if you are looking at it here, when we encounter an empty cavity, most of the time we will encounter a total water loss, and there will be a sudden free drop of the drill rods, and the penetration rate that we can advance our drilling will increase tremendously. This indicates an empty cavity, and in this case, we will adopt a higher slump LMC. to allow the grout to flow without creating too many boreholes. We want to be able to fill out the cavity using the least number of drill holes. So in this case, there will be a pressure limit, but because it's an empty cavity, the volume limit is simply the cavity volume limit, unless the objective is not to trip the cavity, right? For scenario 2, whereby there was no water loss, but there is a sudden increase in the penetration rates, this indicates that infill cavity, the cavity has already filled up with some material inside. In this case, we will choose a lower slump material, lower slump LMC, in order to have more control over the injection. The parameter will be both pressure limit and the volume limit. And the volume limit is a function of what is the size or the idealized diameter that we want to achieve. In scenario 3, of course, if we don't pick up any cavity, then we just backfill it back with OPC grout of cement bentonite. On the quality control side, all our drill rigs, similar to the fissure grouting, we fit with our data logger system, and we also fix the depth sensor onto our drill rig. I will show you all how it will help us in identifying the geological formation later. In the concrete pump case, we fitted the concrete pump with the volume counter and also the pressure sensor. Similarly, all this information are also flowing into our data logger system, where we can monitor it real time. Traditionally in Singapore, for a long period, when we are dealing with the cavity grouting, most of the time we use a soil investigation method. So it was treated as part of the soil investigation works, and when the soil investigation pick up the cavity or the limestone, then the SI contractor will carry on to backfill the thing with the cement grout. The limitation is because SI is creating a smaller borehole that can only be injecting pressure grout at a lower pressure, and this grout is highly flowable as per what I mentioned just now. However, SI method is very good in picking up and be able to recover the core sample for the proper identification. So in this case, in a large cavity, this free flow of grout will be uncontrolled. And it will be hard to exercise control that we can achieve the objective that we want. In the case of the slump zone, because the material is so soft, the grout will just frack the soil and flow freely inside. Compared to the compaction grouting, in the large cavity whereby we are using a much stiffer material, we can control by the volume of injection and mainly work by the displacement methods. So we are also able to form all these reinforcement column inside the slump zone. The main differentiator between these two is the other differentiator is also soil investigation typically are slower because of the coring process and also sample collection process. Compaction grouting can be 3 to 5 times faster, and this resulted also in typical saving of 15%. The deeper the borehole, the saving tends to be higher. But soil investigation, like I mentioned, is able to carry out all the soil sampling and testing, which can be a minimum requirement for any projects. But compaction grouting, we are not able to collect undisturbed sample. However, for the compaction grouting method, we are able to actually carry out acid tests on the rock cuttings to indicate the presence of the limestone. So we roughly can detect where is the limestone. So both methods are useful in the case of cavity treatments. I would take them as more complementary because of the high variability of cavity. It is often quite difficult to just adopt one method. So both methods will complement each other, and this will work well. Next, I'll move on to 2 case studies. First case study is rock fissure grouting for a shaft construction in Singapore, followed by another case study, which is the cavity grouting in Singapore. This is the typical rock fissure grouting layout that we have. Green color is actually the soil that requires temp grouting, which is not our focus today. Yellow color is the curtain grouting that we carry out. and blue color is the base grouting that we carry out. So on the plan view, you can see the spacing, and typically 2 layers of curtain grouting are placed in. The spacing, point-to-point spacing are typically about 1.8 spacing, with a targeted influence zone of around 2.5 meter. The methodology that we adopt in this shaft is that we start with MFC. However, by monitoring closely on the data logger, if we do not see a gradual pressure build up or a gradual reduction in the flow rates, after a while, we will actually switch it to lean OPC. And if lean OPC still do not see the reactions of the ground, that we see a gradual increase in the pressure, then we will further switch to the thicker OPC. This is obviously for first economical stage, because we do not want the ground to flow beyond our targeted ground zone. So when it is so flowable, we switch to a bigger particle material. Ellie has presented earlier to you all about all the data that we collected through our data logger system. Besides providing a real-time monitoring so that we can adjust the ground mix and adjust the pressure sequencing on real time, we are also taking all these things to actually plug into Excel, and we can actually plot out stage by stage what are the key parameters that we want to monitor. So for example, we can monitor the average intake of ground per meter per stage, and we particularly like to see a trend of reduction between primary point and secondary point and tertiary point, meaning as we go further and further, the secondary point in between of two primary points actually have a lower intakes, indicating that the ground is filling up the void. We also look at the total intakes per point per stages. The other key parameter that we like to look at is, as we are progressing from primary point to secondary point to tertiary point, the percentage of the stages that is terminated by pressure increase. This also indicates that the fissure in the rock mass are gradually being filled up. Lastly, also, obviously, the Lujan test per stage, per ground point. The other thing we are also monitoring is to plot the average Lujan that we are able to monitor throughout the grouting periods. In this case, I'm plotting in monthly basis, but we do it on a weekly basis, and we want to see the trends that is coming down. And also, if you can see here, the average ground per meter is dropping. So this indicates that the grouting strategy is working. Otherwise, we would be adjusting the strategy accordingly. So once we finish the primary point, secondary point, and tertiary point as intended, we plot this thing in a plan view and a side view in a 3D modeling. And the size of the bulb actually indicate the volume of the injection, the ground intakes. The area with the biggest bulb typically indicate this area are the area that is problematic. So based on that, we actually carry out additional point in order to seal up all the gap. So in this project, we carry out about 127 points, and after that we added another 6 points on the weak zone. Total ground volume is about 1.9% of the treated rock volume. Next, I will bring you all to a cavity grouting job using compaction grouting methodology that we have carried out in the infrastructure project in Singapore. Well, you are looking at the video playing on the side, which shows you all the type of material. On the left-hand side, you can see that the challenges is that because the cavity actually present a slump zone at a very deep level, at about 40 to 50 meter, and eventually the deepest that we have to treat even go up to 90 plus meter. So this material itself is not able to be stabilized by polymer. So the bolt pile is not able to advance with a stable borehole. It keeps collapsing at the same level. So after facing this difficulty, we went in and then we worked out some proposal based on the compaction grouting method. So what we did is that we work out the primary point that we want to form reinforced columns surrounding the slump zone in order to enable the borehole to stabilize. And this actually go through an observation method whereby we will carry out a primary point based on our experience in the area, and then we will see whether the bore pile is progressing well. If not, there will be chances that additional pile will have to be added, and then additional pile will have to be added. Now this is of course in the worst case scenario that we need to add additional, but one key point is that within the same project, even for different bore pile, the variations of the cavity feature are too much. It's actually too much for us to have a standardized design. So the observation method and the process engineering is very important for us to execute the jobs. So in terms of the process engineering we put in here, the soil rock level is actually recorded by the operator, similar to an SI method whereby the operator will record down. So, but on top of that, the data that is recorded by operator is used to correlate with the data acquisition system that we have from our drilling rig, and also we also correlate with the volume of the mortar that we can inject. So this is what is shown on our real time on our screen. So if you can see here, as we advance the borehole, the feed rate stayed at about 10 meters per minute. So we can advance the borehole at this similar speed. And subsequently, when the hit rock, it will typically drop to 3 to 5 meters per minute of penetration rates. And in between, we may pick up suddenly a material that will allow us to just push it and reaching about 15 meters per minute kind of speed. That indicate that the material is very, very soft and is actually lying between two layers of the rock. After that, what we do is we have a layout plan that based on the detection, we plot out in cross section wise where are the slump zone and where is the rock and where is the soil. So if you can see, green color actually represent the cavity and the slump that we pick up through the drilling, and also gray color represent the rock, and brownish color is actually the soil. And this is actually what we install surrounding a perimeter of one single pile. Within one single pile, this amount of variable is actually present, which is the reason why I was saying that there's a limitation, because this kind of variability will not be represented by a few number of borehole that is commonly being seen in. But of course, once we do this, we then plot on the plan view based on the amount of the grout intakes, what is the idealized diameter that we want to achieve. So in this case, we wanted to achieve actually about 1 meter of diameter to form the closure. And when we found that one of the pile is actually having an idealized diameter of less than 1 meter, then we decided to actually carry out another verification point here. And if we pick up another slump zone, we would have treated additional column here. However, in this case, the verification might actually indicate that there is no further soft zone, and that is where we stop our grouting and we move on. Lastly, I would like to make a few concluding remarks. In the earlier case whereby Ellie has presented, a lot of times the grouting strategy is also limited by what type of rocks that we are dealing with and the geology that we are dealing with. And the delivery method of the grout is inseparable from the quality of the grouting works. All these works hands in hand. And hence, the balance will be required amongst the target of productivity and the cost in the face of the constraint of the rock quality. Modern engineering actually are very lucky to have a lot of real-time monitoring. So as we bring in more and more real-time monitoring, more and more data are being given to us. This actually provide insight into how the ground is responding to the grouting program that we are having. Taking that data, putting it into process engineering will allow a timely review and adjustment to the grouting strategy And in the case of the compaction grouting, the grouting intensity, do we need to increase the grouting intensity? Do we need to add another row? Do we need to increase the pressure? All this can be done in an overview once we feed this into this analysis data. Lastly, for the limestone formation, compaction grouting do provide a faster speed at a lower cost and is able to carry out a control injection as compared to SI coring. So it can work as a complementary method after the SI coring or SI method. SI soil investigation already pick up limestone formation or cavity feature that has to be treated. With that, I end my presentation today. On the upper right hand side, you can see a QR code, and we are looking for your feedback. If you guys are available, please help us to scan the QR code and provide your valuable feedback to us. With that, I hand back to the host, Beatrice.
Okay, thank you. Passing back to Leslie for the Q&A. Thank you, Leslie.
Okay, thank you, Tristan and Luna, for a very interesting presentation. You covered the fissure grouting as well as compaction grouting very, very well, and it's a very useful reference for our, I think about 400 people attending this seminar. So it's a treat, really. So the floor is now open for questions. You can either raise your hands or type your questions in the chat box. So